In this exercise, we will look at forces that act on charged particles. Specifically, we'll take the example of rain droplets in a thunderstorm, which can be charged. If we consider, for example, a single rain droplet with a positive charge, then in the absence of any other droplets, there will be no net charge, no net force acting on this droplet other than gravity, which we will not consider in this example. But now if we add a second raindrop to the right, and I call the charge on the first droplet Q1 and the charge on the second droplet Q2, and for now I will choose the charges to be equally large, and I set the separation between the two droplets at 2 times A, then forces will start to act on the two droplets. They will start to repel each other. So there will be a force acting from the right droplet on the left droplet, pointing to the left, and an equally large, but opposite in direction, force acting to the right on the right droplet. This force is the Coulomb force, and we can write this as follows. So F equals a constant times Q1 times Q2 divided by the separation squared, and the force acts in the direction of the separation. This K is a constant and can also be written as 1 divided by 4 pi epsilon naught, where epsilon naught is the permittivity of free space. Now in this situation, the separation between the two charges is A, as 2 times A. So that means if R equals 2A, R squared is 4 times A squared. So the magnitude of the force, F, will be K times Q1, Q2 divided by 4A squared. So far so good. This is the situation for two droplets. Now things become interesting. I add a third droplet up here. And here we will choose a charge Q3. But again, the charges are equally large. The vertical separation I call B. And in this situation there will be two forces acting on the top droplet. One from the bottom left droplet, and that points in this direction, where I call this angle over here theta, and by symmetry you see that the same angle theta appears over here. Likewise, a force acts from the bottom right droplet onto the top droplet, pointing in this direction, and the same angle theta also appears over here. Now the total force acting on the top droplet will be the sum of those two forces, which you can draw as follows. It's a vertical force. We call this F total. And it is the sum of the two vectors. And by symmetry in this situation, you can see that the horizontal two components of the two vectors will cancel each other. That's because the charges are equal and the horizontal separations are equal. As a result, we only need to count the vertical components of the two forces and add those in order to get the magnitude of the total force. Now let's look at the magnitude of one of these forces. Let's take this one here on the right. So the general formula for the Coulomb force is still the same, but now we have to write it as follows. The magnitude F will be K times Q1, Q3 divided by the separation between these two charges. Now in this case, the separation R equals the square root of A squared plus B squared, so we get A squared plus B squared here in the denominator. However, we are interested in the vertical component of this force. So in order to get the vertical component, so this part, I need to multiply this magnitude with the sine of theta, which is nothing but the opposite lag divided by the hypotenuse. So sine theta in this case will be b divided by the square root of a squared plus b squared. And this we have to put in front of the force to get the vertical component. So Fy, the vertical component of the force, will be b divided by the square root of a squared plus b squared times k times q1 q3 divided by a squared plus b squared. Now finally, in order to get the magnitude of the total force, I need to take this vertical component twice, because each of the force adds the same vertical component. So we know that the total force, F total, will be 2 times b over the square root of a squared plus b squared times k times q divided by a squared plus b squared, where I've defined q to be the equal charge of all three droplets. This concludes this example.